Methodical. Human language is messy. We communicate through complex, unstructured strings of text, full of idioms, irregular spacing, and subtle context. But neural networks operate strictly in the realm of mathematics. They require rigid, structured numerical tensors to perform their calculations. Consider developing an AI model for sentiment analysis on user feedback. To determine the sentiment, the model must isolate and weigh specific keywords, identifying terms like good or bad. This graphic highlights the required mechanism. Extracting those keywords means breaking the continuous user-provided sentence down into smaller, meaningful components. We call these individual pieces tokens. The software component tasked with parsing raw text into these distinct pieces is known as a tokenizer. This flowchart details the three primary methodologies a tokenizer uses to generate its output: word-based, character-based, and subword-based tokenization. Without this process, natural language processing is impossible. Tokenization is the mandatory translation layer that bridges human concepts to machine-readable data. The most intuitive approach is word-based tokenization. Here, the tokenizer scans the text and splits it every time it encounters a space, treating each distinct word as an independent token. This diagram shows how a sentence like, "You are learning tokenization," is divided directly into 4 individual word strings. The engineering benefit of this method is interpretability. The semantic unit remains intact, passing clear, dense meaning to the model. However, treating entire words as base units creates a massive computational footprint. Every variation of a word must be stored as a totally unique entry in the model's vocabulary. This code execution demonstrates the bloat. Using traditional natural language toolkits like NLTK or Spacey, the plural unicorns and singular unicorn are mapped as entirely different tokens. The model has no inherent play to know they are related. Character-based tokenization swings the pendulum the opposite direction. It fractures text completely, splitting it down to individual letters and punctuation marks. The vocabulary shrinks drastically, down to just the alphabet. But single characters convey almost zero semantic meaning on their own. Furthermore, treating each character as a unique token causes the input dimensionality to explode. Short sentences turn into massive sequences, severely taxing the memory and processing power of the model. Engineers require an approach that preserves the semantic density of whole words, without the vocabulary explosion caused by minor variations. Subword-based tokenization solves the dimensionality paradox. It leaves highly frequent words intact, but fractures rare words down into smaller, meaningful structural subwords. This diagram illustrates the logic in action. A complex word like unbelievable gets surgically divided into its prefix, root, and suffix. This list details the 3 core algorithms modern NLP systems use to determine where exactly to make these splits. The word piece algorithm relies on rigorous evaluation. It calculates the statistical benefit of keeping 2 symbols merged versus splitting them, ensuring every fracture serves the model's efficiency. The unigram algorithm takes a subtractive approach. It generates a massive list of potential subword combinations, then iteratively trims away the least useful pieces based on how infrequently they appear in the training corpus. Sentence piece treats the entire input sequence as a raw stream, including the spaces themselves, segmenting the data into manageable parts and assigning them unique IDs. Because words are now broken into fragments, these algorithms must apply specific visual markers to the tokens so the model knows how to reassemble them accurately. This output shows an XLNet tokenizer in action. Notice the underscore prefix attached to subwords like IBM and taught. This underscore acts as a flag, indicating that the token was preceded by a space in the original string. Conversely, the fragment ization appears completely bare. The lack of a prefix instructs the model that this token must be glued directly onto the preceding subword without a space. By recycling these structural fragments across the entire corpus, models can process a virtually infinite variety of language while keeping their internal vocabulary strictly finite. Bridging the gap from linguistic theory to functional software requires a concrete pipeline. In PyTorch, engineers leverage the Torch text library to process datasets at scale. This graphic outlines the necessary sequence. Instantiate a tokenizer, build a vocabulary over your entire dataset, and assign a unique numerical index to every token. This diagram demonstrates the getTokenizer function. You feed it a string like Introduction to NLP, and it yields a Python list containing the isolated, normalized string tokens. To handle massive data blocks efficiently, developers write a yieldTokens function, applying the tokenizer across an iterator to process text sequentially without overloading memory. The output of that generator is passed directly into the buildVocab from iterator function. This is the mechanism that creates the actual numerical ledger. This dictionary maps each string token parsed from the dataset to a rigid integer. The word NLP becomes index 1, PyTorch becomes index 2, and so on. The final processing step replaces the human-readable string lists with a sequence of integers drawn from this exact dictionary map. This terminal output shows the final result. The string list containing introduction, to, and NLP is structurally transformed into the integer array 14, 19, 1. Those strings no longer exist in the pipeline. That array of integers is the only form of language the neural network's architecture can actually ingest. Even with optimized Subword algorithms, a model in production will eventually encounter text strings it never saw during its training phase. This is known as the out-of-vocabulary problem. This code block solves it by assigning an unknown token, or UNK. By calling setDefaultIndex, you ensure that if the model stumbles on an unrecognized word, it maps it to this dedicated fallback integer, instead of crashing the process. Next, to give the model a sense of absolute boundaries, special structural tokens are injected. BOS, or beginning of sequence, is appended to the start of the list, and EOS, end of sequence, is appended to the finish. Finally, because neural networks process matrices of fixed dimensions, the pipeline applies padding. Shorter sequences receive empty pad tokens until they match the exact length of the longest sequence in the batch, forming a perfect computational grid. Raw, chaotic user feedback has been isolated, fractured into subwords, mapped to a numerical dictionary, bracketed with boundaries, and padded into strict uniformity. Getting the language into a form the math can process dictates everything that follows. Mastering tokenization is the critical first requirement for engineering high-performance natural language systems.